So I'm very happy to introduce Andrew Scott from Telestream, who's going to be diving into PTP, which is really the key innovation that allows ST2110 to work. So take it away, Andrew.
Okay. Thanks and good morning. So I'm going to talk about PTP. There's a nice diagram at the back of the room, shows the technology pyramid for media nodes, and PTP is second from the top, so it's essential to the operation of these networks. So let's talk a bit about PTP. So PTP stands for Precision Time Protocol. It's a 20-year-old standard now. It was originally developed by the IEEE, and the original applications were more about industrial automation, telecom networks, finance networks, where they needed more precise timing than NTP, which is sort of the traditional time protocol that we use on our PCs. The video industry picked up on PTP a few years down the road. So the first standard where video is using PTP was the SMPTE 2059, which was published in 2015. That was based on the second version of PTP, so IEEE 1588, 2008. So that's PTP version 2. There is an older PTP version 1, not used at all in video implementations. I think it might still be used on some audio networks. So Dante uses PTP version 1. You don't really want to use them together. It's not backwards compatible. The most recent version of 1588 is from 2019, so-called version 2.1, and it is backwards compatible. So you can have networks running both version 2 and 2.1, and they will interoperate with each other. Some of the terminology has changed a little bit. So if you look at the original standards and some of the terminology you'll see in products, they refer to master and slave. Those words not so good anymore. So SMPTE is the first organization to use alternate terminology. So we'll use leader instead of master and follower instead of slave. So in this presentation, I'll try to use those, but there's a couple of places where we dip back into the old terminology. PTP operates over IP networks or other network types. So I've only ever seen it over IPv4. I don't really see IPv6 networks, but it can work over there. PTP can work over alternate layer 2 networks, but like I say, for the most part, it's over IPv4. It uses the UDP instead of TCP, so it's unacknowledged messages, they could potentially be dropped. We use 2 dedicated port numbers, port 319 and 320, for different message types. So I'll talk a bit about this in the next slide. We have event messages and general messages that have different prioritization. They can come in on different port numbers. PTP can use unicast or multicast, and if we use multicast, again, there's an assigned address that's used that everybody knows how to interoperate with that. There's a handful of specific message types in PTP. There's more than I've shown here, but these are the common ones that you'll see. And as I've said, there's event message types and general. Event are the higher priority ones. And we'll talk about in the next couple of slides how the timing is synchronized using these specific message types. I'll also talk about how the announce message is used to establish our synchronization hierarchy. Within the switches in the network, they use a technique called differentiated services, or diffserv, to enforce that priority. So the event messages are the most important. They have the highest priority in the network, even higher priority than our media, our video and audio itself. So let's look at how the messages are used to synchronize clocks together in the hierarchy. So this diagram is taken straight from the 1588 spec, and it's a familiar diagram for those who've looked at PTP. It's an exchange of messages between the two sides. So this diagram shows master and slave, but again, that's leader and follower. The process is initiated from the leader side by sending a sync message. And these are sent periodically. I'd say for video networks, the default rate is 8 messages per second. So 125 milliseconds apart. We'll send a sync message. That sync message could contain the timestamp of when it was transmitted, and we call that in the diagram here T1. So I say could because it requires hardware support. So there's chips, that support the physical layer, the MAC layer for Ethernet, can do that hardware-based timestamping, and they're able to insert the timestamp in the packet as it's being transmitted. If that's not possible, the timestamp is still recorded by other hardware, and we send a follow-up message sometime later that does contain the value of T1. So T1, even if it comes in the follow-up message, it's the timestamp of the sync message, not of the follow-up. On the follower side, we receive that and mark it as T2. So now we've got the difference, T2 minus T1. That's the time it takes to transmit that message across our network. Basically, it's the latency through the switches, through the transmission cables and so on. But our master and our leader and follower clocks are not necessarily running the same time. That's what we're trying to do, is get them together. We need to have another message pair going in the other direction to measure the opposite offset. And that's done through another pair of messages, delay request and delay response. And again, the delay request has the timestamp of when it was sent, and the leader side, when it receives that, it can figure out T4 and send that back in the delay response. So after this full exchange, the follower side has all 4 timestamps, T1, 2, 3, and 4. And from that, we just do a little bit of math and can compute the corresponding delays. So T sub MS, I guess master slave, but that's the master to slave or the leader to follower delay is basically T2 minus T1. The follower to leader delay, or T sub SM here, is T4 minus T3. The mean delay is simply the average of those two. So that's assuming that the propagation delay is symmetric, the same in both directions. I've kind of oversimplified the equations here a little bit. There's a bit more to it because you can have compensation factors for asymmetric delay. But the basic calculation is here. The offset then is the difference between those two divided by 2. And so once the follower side has the offset, the mean delay, it can essentially adjust its clock so that it's tracking the leader at this point. So now we've synchronized our clocks through the exchange of those 4 timestamps. So I mentioned clocks. The terminology used in PTP is to refer to each node in the network as a type of clock, right? So your camera can be a clock. The different clock types, we have ordinary clocks, which is pretty mundane way of calling it, but an ordinary clock is simply any PTP node that has a single port. The standard says it can operate as either the follower or the leader, but typically, especially in video networks, we will enforce that certain types of nodes are only going to operate as leader only and others as follower only. So a good example of that would be, your camera, your microphone. If it's a 2110 type device, you don't want it to be the grandmaster, the clock that's synchronizing the network. You want a special device at the top of that hierarchy that is, perhaps synchronized to the GNSS satellites in the sky. It's got a disciplined oscillator. So we enforce this hierarchy in video where we have leader-only devices and follower-only devices. A boundary clock is the terminology for PTP-aware switches in that hierarchy that are able to basically terminate one path of PTP and initiate a new one. So if you think of a multi-port switch, a 32-port switch, one of those ports will be the follower side synchronized to its leader up above, and the other 31 ports are now leaders for the devices below. Boundary clocks are great because it gives us scalability in large networks. Instead of having thousands of devices all talking to the same leader, we have this hierarchy where boundary clocks in between are essentially the leaders, at intermediate points in our networks. The IEEE standard also designates a type of device called a transparent clock. I won't really talk about it here because I've got a 25-minute presentation and not an hour-long presentation. PTP is a lot more complex than I'm giving you the highlights of. I would say transparent clocks are simpler devices. They're PTP aware in that they're able to overwrite the timestamp and messages that go through, but they don't really participate in the protocol other than that. And say the boundary clock architecture is the way to go. And specifically, I would say the common architecture that you're seeing in media networks is something like this, where at the top we've got our grandmasters. So these are the leader clocks that are typically synchronized with GNSS systems. So GNSS is the umbrella term that includes GPS from the United States and the other satellite systems elsewhere in the world. So GLONASS in Russia, Galileo in the European Union, Beidou in China, and so on. So the neat thing about the global satellite systems is each of the satellites has an atomic clock inside it. And so if we're getting signals from multiple satellites, we can get a very accurate time of day by synchronizing to that. So our grandmaster devices at the top will have an accurate time of day to work from. In between, I've got a switch architecture here, spine nodes and leaf nodes, the terminology that's used. What we're doing is we're creating a mesh of switches that gives us a level of redundancy. So you'll see by the color coding that I've got here, I've got an amber and blue network. Basically, I've got a redundant path. And as Wes mentioned earlier, the 2022-7 protocol defines how we can have a duplicate copies of our 2110 packets, our video and audio, and in case there's packet loss or network outage on the amber network, the packet from the blue network will still make it to our destination, and we can still reassemble that video or audio signal. So my device is at the bottom. A media node is kind of the generic term, can be a receiver or a sender. A camera is obviously a sender. It's originating content. A multi-viewer display device is a receiver, right? It's receiving that video and audio and doing something with it. They're connected to, if we have two network ports on each of them, they can connect to both the amber and blue networks and give us that level of redundancy. The other thing I'm showing here is a sync generator that, again, is connected at that bottom edge of our network to the PTP network. It will be a follower device taking PTP in, but that clock in that sync generator will be synchronized all the way back up to our grandmasters. And so any black burst or our legacy synchronization signals that are required for legacy devices will be completely synchronized with our PTP wear devices. So for the next few years, I anticipate there will be, a lot of hybrid networks where you've got to interoperate between, legacy equipment that relies on black burst and modern devices that use PTP. This is the bridge between those two worlds. All right, so in this diagram, I've got two lead clocks at the top, the grandmasters. How do we know which one is going to be the one clock that we're synchronizing to, right? If we've got multiple clocks for redundancy, the way this works is using the announce message that I showed earlier. An announce message is sent periodically by that lead clock, by the master. It has 6 pieces of information in the announce message. A couple of them, priority 1 and priority 2, they're user configurable devices, parameters. So you'll see in a configuration screen, on a grandmaster type device, you'll be able to set priority 1 and priority 2 values. So this gives the network administrator a way of tuning the behavior of the network. Typically, you would set priority 1 to be the same. And the reason is you want the next few variables to be the determining factor of which GM is taking over. So the clock class, clock accuracy, clock variance, collectively they're called the clock quality. Basically, it's a measure of how good our synchronization source is. So in this case, there's a specific value that's used for I'm locked to GNSS. Let's say, something happens. We have bad weather, we have a bad signal, and that signal degrades. If our first grandmaster that is synced to GNSS goes into holdover mode, the clock class changes value, right? The announce messages coming from that GM will now have a different value, basically saying, I'm no longer synced to GNSS, I'm in holdover mode. If the other GM is still synced, it will have a higher clock class. Well, it's actually a lower number, but a better clock class. And because these 6 priority values are used in order, it's now the better clock and it will take over. That algorithm, it's called the best master clock algorithm, or the BMCA. And a little state machine for the BMCA basically shows like this. When a master starts up, it's going to start listening for announce messages. And if it doesn't see any announce messages at all, or if it sees them from an existing GM that's got a worse, lower quality than it does, it will take over. It'll start sending its own announce messages. So if each device in our network understands the BMCA, they'll basically be able to see the announce messages coming from one master. The others are just listening. They're in passive mode. And if a new master takes over, you'll start to see announce messages from that device. And that's how we know that we've switched from one GM to the other because of a change in the network. Another configuration value that we've got when setting up a PTP network is something called a domain. And a domain it's just simply a numeric identifier. It's an 8-bit value specifying what our logical PTP network is. You can have multiple domains coexisting on the same physical Ethernet network. And this is kind of useful because you could have different devices or device types attached to different domains. I could have one for my audio devices and a different one for my video devices. And why that may be useful is because of, I'll show on the next slide, you can have a different profile for those different types of devices. Every PTP message has a common header, so whether it's announce or sync or whatever, and in that common header is the domain number. So it's very easy for a receiver to be able to distinguish, is this my domain or is it someone else's, and accept or discard the message as appropriate. So with respect to profiles, a profile is simply a collection of attributes and options for a PTP network, for a particular application. So a profile can define the allowable message rates. So earlier I mentioned that announce messages are coming once a second, our sync messages 8 times a second. Those are actually variable. There's a minimum and maximum value that's defined in particular profiles. So depending on the application, we might have different message rates. The other thing that profile can often identify is a communication model. So I've mentioned earlier that multicast or unicast operation can be used for PTP, or a mixture of the two. Right? A mixed mode is commonly used in video networks. The 3 main profiles that you'll see in our world, mostly 2 I would say, but the IEEE standard defines a default profile for, it's given the name the Delay Request Response Default PTP Profile, but it's the IEEE standard. In SMPTE 2059, which we've talked about before, is where we modify some of those parameters. So sync messages are sent faster. We want our video devices to synchronize more quickly than the default. So the sync message rate is higher in the SMPTE profile than it is in the IEEE profile. I'll talk a bit more about the SMPTE profile next. There's more things that it adds as well. The audio standard AES67 has a different PTP profile. They call it the AES67 media profile. Again, slightly different message rates and allowable communication modes. So between domains and profiles, that allows us some flexibility in setting up our PTP network. There are other profiles, for the telecom world and so on. So there's PTP Grandmaster products out there that support those industries. I would say in the video world, you're not really going to see those. It will mostly be the SMPTE profile, SMPTE 2059. So I mentioned it defines what our message rate limits are. It also defines 3 different communication models. So multicast is the simplest. It's the least amount of configuration because the devices are using that one well-known multicast address. So it's very easy to set up, but it's not very scalable. If you think of that message exchange I showed before, right? If we're doing multicast, that means every follower is sending delay requests that every other node is going to see because they're listening on that multicast address. Unicast requires a bit more configuration. Basically, you've got to program all of your devices with the correct IP address so that the followers know which leaders to talk to and so on. So full unicast is probably the, maybe the most scalable, but it requires the most configuration. And unicast, pure unicast also has an additional process that I won't describe here other than saying you have to ask the leader, can you please send me messages? So you get a grant. And part of that negotiation process, you ask for sync messages to come at a certain rate. And so a leader could potentially deny that grant, if it's starting to get overloaded. And that's where mixed mode comes in. So mixed mode is a really good creation in the SMPTE profile. Basically, it says that the announce messages, the sync messages, and follow up if we need that second step, and management messages, they're sent by multicast, right? So all of my followers can use the same sync messages. I don't need to send one to each follower individually, just send one unicast sync message, everybody will receive it. But each of my followers needs to send their own unique delay request message back and get a unique delay response. So that part is unicast. That's what makes it mixed mode. So this is probably the most useful combination, multicast and unicast together. And then in my last point here, the other thing defined in the SMPTE profile is something called a synchronization metadata TLV. So TLV stands for type length value, but basically it's a way of sending metadata from the leader to the followers. And the kinds of things that are in those metadata packets are information for all my followers to be able to reproduce SMPTE timecode in those devices. The example I've given here is the jam time. So not such a big deal in Europe where we use 25 frames per second, but in North America where we have 29.97, we have drop frame timecode, which is awful to work with, but one of the byproducts of that is typically broadcast stations, 2 in the morning each night has to do a jam. Basically, we get some accumulated difference between time code and real time of day. And so in the middle of the night where there's not many people watching television, we'll do a jam and, skip a couple of frames to get back in sync. When that time is, that can be communicated. That's one of the values in the synchronization metadata packet. There's about a dozen or so items, but it's useful information specific for the video world. So that's why it's defined in the SMPTE standard and not in the IEEE standard. All right, I'll finish by talking a little bit about some best practices in testing. We've had a few years now, a lot of the interoperability events. Wes mentioned one we had just a couple of weeks ago in Germany. I would say that we're reaching a point of maturity and stability with these networks. And some of the common lessons that we've learned are, sort of how to create an effective media network. I think the amber blue technology, that style where we've got the redundant network and the leaf spine architecture widely used now. And I think that's sort of the common style that people are deploying in their networks. It's important to have PTP aware switches. And so I think, we've got general purpose Ethernet switches, but the major switch vendors are all now catering to the video industry. We've got PTP aware devices, and they can serve as boundary clocks. I would say, again, one of the lessons we've learned is that the boundary clock architecture, using that in our system, is a tremendous benefit for scalability. It doesn't overload the grandmaster with receiving delay request messages from thousands and thousands of followers. We can have a level of scalability by deploying boundary clocks in our network. And then lastly, use the SMPTE profile and stick to the standard default message rates. I think we start to stray a little bit when different devices deviate in the configuration and have slightly different message rates. Just stick to the SMPTE defaults and things seem to work pretty well. In terms of testing, commissioning and troubleshooting, say we've got a class of products out there now that can do a monitoring of PTP networks, measuring. They typically work by being active participants. They are follower devices in their own right and exchanging in the PTP protocol, talking to the leader on that network. Because the follower side, if you remember before, has those timestamps, the T1, 2, 3, 4, we can now use those, as a measurement tool, not just to adjust our clock, but we can generate graphs to show how those are changing over time. Do we have, drift happening on our network? Are there periodic hits? Things like that. It's very easy to see with a visual tool, and we get that data just by being an active follower on the network. The other type of troubleshooting tool that we'd use is more of a passive, where we're just capturing the data, as an observer, and using post-analysis tools for that. So Wireshark, everybody's familiar with that one. There's some great features in Wireshark for looking at PTP and creating graphs from that and so on. Okay, I think my 25 minutes is about up. If there's any questions, yes. Oh.
Hi. If you can go back to the slides with the multicast and unicast.
This one, maybe?
Yes, this one. If I'm in a network of unicast, how can I change the grandmaster, because it's already only unicast configuration? So if there is another grandmaster that is going to take over, I don't know about it because I'm configured as a unicast, right?
True, yes. So the way unicast works in that environment, you typically have a list of possible masters. So the unicast discovery list. And so if you stop receiving announce messages, right, which you should get, there's an announced timeout value. Typically it's set to 3. So if we're getting announce messages once per second, after 3 seconds, if we get none, just go to the next value in the list and initiate the grant negotiation.
There is a list, like a
exactly.
I don't know, primary, secondary, or something like this.
Yeah, it can be more than 2 items in the list, 8 possible masters or whatever. So yeah, you simply wait till the announced timeout and then just move down the list. Yeah.
All right, Andrew, thank you very much.
Thank you.